This is part 2 of section 4.2. We just talked about some properties of logarithms, and now they're going to ask us to calculate some logarithms without using a calculator. Okay? In fact, your calculators will not do a logarithm with a base other than either 10 or e, and we're going to talk about that in the next section. Okay? So I have our properties written down here. Let's look here. Log base 11 of 11. Well, what does this look like? It looks like I have this one. I have 11 and 11, so these two are the same. I don't have a visible exponent on this 11, right? Okay, but log base b of b, log base 11 of 11 is 1. This is always a 1. Okay. Now here's one that's a little bit more tricky. Log base 3 of 27. When I just glance at this, I don't have anything that will work directly because all of these require having the same base somewhere other than this one, and I don't have a 1 in here. Okay, so what I want to do is I'm going to ask myself if I can rewrite 27 as 3 to a power. And 27 is 3 cubed. So I'm just going to rewrite this right now. I have log base 3 of 3 to the 3rd power. Now I have something that is in this form. My base and the base of my argument are the same. And this property says that if this and this are the same, then your answer is the exponent of the argument. So this answer would simply be 3. Okay. Log base 5 of 5 to the 7th power. I have the same base here, and here I have precisely this pattern. So my answer is x, which is the exponent. So this is 7. Okay. 7 raised to the log base 7 of 23. The only property I have here that starts off in exponential form is number 4. So let's see if we have this. This is a 7 right here, and so is this, and that is required that these two be the same. And then this says our answer is the argument of the logarithm, which is 23. So this answer is simply 23. Okay. So let's talk about some graphs of these things. Just some basic characteristics. In the previous section, we did the exponentials. We talked about the graph of f of x is equal to 2 to the x. And we talked about the graph of f of x is equal to 1/2 to the x. Okay? And we're going to talk about the logarithms of something very similar to these. Okay? So what I'm going to do on this one is I'm going to worry about log base 2 of x. So I'm going to graph f of x equal to log base 2 of x. Notice this and this are the same. And then over here for this one, I'll be talking about f of x equals log base 1/2 of x. Notice that these are the same. And the reason I do that is because we do end up with two separate graphs based on that one difference. The x-intercept of a log is always 1, and there's never a y-intercept, okay? The y-axis is a vertical asymptote. If b is greater than 1, so our base is greater than 1, which is what I have right here, then our function is increasing. It's going to be going up. If our base is between 0 and 1, the function is decreasing, so it's going down in this case. And the graph is smooth and continuous. Now, one thing we do know, and I've told you a couple of times, is that these two things are inverses, okay? So if you go back and you look at what we did for in section 4.1, we did a t-chart for this, and our values, we did -3 and 1/8. -2 was 1/4. -1 was 1/2, and I'm just directly pulling these from the previous section. Okay, so these go along with this. You may remember, I hope you remember, that if you want to graph an inverse, all you have to do is to switch every x and every y. So I'm going to reverse each of these. Okay, so when I graph these, I'm going to do 1/8, -3, 1/4, -2, -1, no, negative, oh, 1/2, sorry, I get a -1, 1, 0. Notice this says that our x-intercept is 1 and we have no y-intercept. Back on the exponentials, we always had a y-intercept of 1 and no x-intercept. So these are backwards as well. They flipped as well. 2, 1, 4, 2, and I don't go out to 8 here. So this graph looks like this. It increases quickly at first, and then it starts to level out and it goes more slowly. Now I want to show you the comparison between this and the exponential. One of the things we learned about inverse functions is that they're symmetric over this diagonal line right here. This, on tracing paper, is the graph of the f of x equals 2 to the x, which is the inverse of this one. And you can see the symmetry here. This is the logarithm. This is the exponential that goes along with it. And I have it turned just a tiny bit, so it's a little bit off, but there you go. You can see this. They are completely inverses of each other. Okay, now the same type of thing happens when our exponential has a base that is less than 1 but greater than 0. Or if you go back and look at when we did this and we had our t-chart, what we had was -3, 8, -2, 4, -1, 2, 0, 1, 1, 1/2, 2, 1/4, and then 3 was 1/8. And again, I pulled these directly from this t-chart that we did in the previous section. These are inverses of each other, so we switch our x's and our y's. So at 8, I'm at -3. I don't have 8 on here. So at 4, I am at -2. At 2, I'm at -1, 1, 0. Oh, yeah, 1, 0, 1/2, 1, 1/4, 2, 1/8, 3. You can see that you're getting closer and closer to your y-axis here. You end up with a graph that's sort of like this. I know I didn't do such a great job of drawing right in there, but I think you'll get the picture. Okay, and if we compare this to the graph of f of x equals 1/2 to the x, which we again did in the previous section, you can see here that this was the graph of our exponential, this is the graph of our log, and you can see that they are symmetric over this diagonal line. Okay. Let's talk about finding the domain of a logarithm. Now, what we said earlier was that the argument has to be greater than 0. Okay, that was part of the definition of a logarithm, which I have right here. See, x, which is the argument, had to be greater than 0. So what this tells me is that in order to find the domain of this, x plus 2 has to be greater than 0. So when does this happen? Just solve this. My x needs to be greater than -2. This is strictly greater than, not greater than or equal to. So when we write our domain in interval notation, it is going to look like -2 to infinity. Now, if they ask you for your domain this is interval notation. If they ask for it in set builder notation, you would write this, the set of all x such that x is greater than -2. Now, all this is saying is that as long as our x value is greater than -2, we're not going to have a problem calculating this. It's going to exist. Now for this one, I have log base 8 of 7 minus x. And again, my argument needs to be greater than 0. So 7 minus x needs to be greater than 0. Since this is a negative, I'm going to move the x over to this side. And I have 7 is greater than x. So that means 7 is as large as it possibly could be. So that means I'm allowed to start at -infinity and up to, but not including 7. Now, it does seem weird saying that your x can be a negative number. X can be negative as long as once you do this arithmetic, you have a positive number on the inside. Okay? So this, in interval notation, would be -infinity up to 7. In set builder notation, it would be x, the set of all x, such that 7 is greater than x.